see you next time. Okay, so it's all right. All right, so here's the third problem. I don't know if it's easier or harder. We have a triangle ABC and we draw the end circle. So let's call it I, right, center. And then we have a point on ABC where angle ASI is 90. This kind of concept looks familiar, or H is the orthocenter of BIC. So I think the orthocenter of BIC makes a parallelogram with the AX center, if I remember. So for the time being, see what that looks. That didn't work. Okay, so let's just do it this way. But yeah, I have a feeling this problem won't be that hard. So let's see. H is just all the way up there. So yeah, let's try to draw a figure so that H is not so far away. Okay. So ASI is 90. So S is the, what do you call it, the Q point. And it's collinear with the midpoint of BC and the antipode of A. So we'll draw those in later probably. So this is S, HS. Yeah, it's the Sharkey double point. Oh yeah, sorry, the Q point, you're right. The Q point would be where the circle with diameter AH meets the circle. So yeah, it's the Sharkey double point. So that means that if we connect these, then it means that this is perpendicular to EF. That's a well-known fact. Okay, so H is the orthocenter of BIC. It also makes a parallelogram with the AX center. So if we drew that, that would be a parallelogram. That's a well-known fact. I've seen it a couple times. So angle AQI is 90. So Q is on HS. That looks kind of new. So I've never seen a point like that before. So this would be Q. Prove that the reflection of I over the midpoint of DQ. This is a very weird problem. Oh. Interesting. So apparently it looks like QD it's saying if we reflect I over DQ, then it should lie on the, right now I'm confused. Oh, it looks like the midpoint of DQ lies on EF. Yeah. Yeah, so I think the midpoint of BQ lies on EF. I can't prove it, but basically, if I take the midpoint of BQ, it makes it look like it lies on EF. Yeah. So that's the first step, I guess, is to prove that. And then the second step is to show that if we reflect I over j, it lies on the circle. But yeah, this is a kind of interesting problem. So yeah, you have the intersection of HS with this circle. It feels like inversion. It feels like this problem might be made for inversion, but I'm not sure. So if you reflect it, if you make a parallelogram, then H prime would be the AX center of ABC. And yeah, we could use the N center, X center lemma. We get all kinds of stuff. So like that. It's basically, the problem is saying that we want to show that QFDE is a parallelogram, because apparently the midpoint of BQ lies on EF. Oh, but it's not necessarily the midpoint of EF, so that's not true. That it's a parallelogram. H, K, and H prime. That's actually a well-known fact, so it's not too hard to prove. It's because trying to remember. I think it's just an angle chase, but let me think about it. Yeah, we want to show triangles HBC and H prime BC are congruent. So angle HBC would be 90 minus angle ICB. An angle, yeah, it's because basically angle H prime CB is 90 minus ICB because it's the right angle. And the same is true with angle HBC is 90 minus ICB. So basically HBC and H prime BC are congruent by angle side angle. Yeah. But yeah, Q is just such a weird point. I don't really know how to use point Q. It's just very odd. But so I wonder, I have a general question. If we have a circle and we have a chord, we're saying that there's some point on the chord where when you reflect it and over that it would lie on the circle. Is there any way to figure out what that point is? So like if I reflect n over r, I want to figure out what the point r is such that that reflection would lie on the circle. How would we find that point? Oh, basically we would drop a perpendicular and then we draw the line with double the distance and see where it intersects. That's kind of how we would do it. So basically, if I take the midpoint of the F, and which is T, and I reflect I over that. Whoops. I reflect I over T. And yeah, we're saying that those would concur. So but yeah, I don't know if that's really that helpful. Let me try it for just a sec. So if I have this point U, and I want to see if there's anything special about U. Yeah, this looks tricky. This looks like a deep problem. We could work on it for like another 10 minutes, but yeah, I think it's kind of hard.
I don't think that the midpoint of GQ lies on EF.
You don't think so?
I mean, yeah, it's kind of weird, and I try on GeoGebra and I move the point A around, and it seems like it's not always lies on EF.
Oh, really?
Yeah, you can try. Or maybe you can just zoom it, so that you
Zoom
can
it.
see it. Yeah,
Okay.
you can make it bigger so that
Yeah,
you
like
can
right
see it.
here. Yeah, you're right.
Yeah,
I got
I mean,
confused.
it's kind of weird. Like, I don't know what's the point Q all about.
It's very close to EF, but yeah, it doesn't. I guess if you start to make it more obtuse, or Oh no, you got to make it a taller triangle, I think, and then you start to see it doesn't lie on it. That's interesting. Okay. So yeah, now I'm really confused. um, oh, yeah, the way I drew it, it's like Q has to lie on this segment. Okay, so we just can't assume that it lies on EF. You both want you both want to try another problem or keep working on this?
Maybe try another one.
All right. Um, this looks kind of. Let's see. Oh, what was this? Sorry. Let me try this. I don't even know where I got it from. Oh, I think this is from the Iranian Geometry Olympiad. I think so. Let's see. Yes. Oh no, it's the same contest. Okay. I don't know why. Oh, it's kind of a long problem. Yeah, okay, so it's okay. So we have a triangle ABC and we draw the end circle. We have D, E, and F, and DI and EF meet at K. So K lies on the A median. That's a well-known fact. This is K. So I'm going to draw the median. All this, we can call this M. So this and we have this. P lies on the end circle, so that DP is perpendicular to EF. Okay, so this looks like the Sharky Devil configuration, kind of. So DP is perpendicular to EF. Maybe it's where it's running this point also. And AP meets omega again at Q. And then BQ and CQ meet it at B1 and C1. Okay, so and then B1, C1 cuts BC at X. This is a lot of points. Let's see. So this would be B1 and C1. X. So the line through the midpoints of BC and EF. Line through I parallel to BC. And KX are concurrent. It's a very random problem. So this is X. We'd have this, KX. Okay, so if KX meets HM at a point J, then basically we want to show IJ is parallel to BC. But yeah, it seems kind of complicated, but just the way the whole thing is. Let me try. Let's try a different problem. I feel like this one's kind of hard. Sorry. I think there was one that looked a little bit easier. Let's see. Like this one looks like it might be easier. So we have a triangle with altitude AB. Oh, it has a symmedian point. Maybe it's not that easy. Didn't realize that. Let's do this one. I just want to try one easier problem today. So this is a different contest. It's a mock geometry. And there we go. So we have a circumcircle omega, and O, I don't think O is the center. I think O is just a point inside it that lies on the angle, that lies on the perpendicular bisector. So we have a point O, not necessarily the center of the circle. And I'm going to draw the midpoint of the side just to do it. Oh, it says M is the midpoint. And we see where line AO meets this circle. Okay, so D is on AB, so that OD is parallel to BC. So that's D. And AO intersects, so we draw the circle COD. Okay. So we have A prime and P. This is A prime. This is P. And we have M, and then we have M, A, and A prime. And it intersects BC at L. AL intersects omega at K. And we want to show that APK is A prime M. Okay. So 21.37 and 21.37. Okay. I would be surprised. I'll check this. These were actually similar triangles. That's 137. And this is 146. So they're not similar triangles. We just need to show that those angles are equal. Let's see, if we move O along, we're going to hit bisector. What happens? A prime M is ALM. So it's kind of, if we draw this point, it's equivalent to saying KEKLP is cyclic. So it's interesting. think about that. P L K E. I wonder if these circles have the same breadth. All right, see you next time. Thanks for joining us. Just you and me, Pascal. Let's see. Let's see if we can solve this one. This looks like it should be doable. So we can move O around. There's a good amount of flexibility in this problem. Can we prove it for a certain special case? Like if O is a circumcenter? MA prime equal MA almost looks true. No, it's not true. Let's think about this. It's perpendicular. A, this is not an antipode of A. That's what makes it confusing. Okay, so I kind of like the idea of showing that this is cyclic because there's a couple ways you could think about that. We'll draw it again. So what if we did it like this instead? Because P is defined very strange. The problem is equivalent to showing this is cyclic. So what if we instead let P prime, so we could define E, it's just AO intersect BC. And so we can define E. Oh, but K and L. So we can define E, we can define L. It's just A, M, A prime, intersect BC. And we can define K. So what if we define P, okay. Let me think about this. So I'd rather define P like this. So it's where AA prime meets the circumcircle EKL. And then we could try to show that DOCP is cyclic. So I could call this like P prime. Somehow I think that's easier to think about. We want to show DOCP prime is cyclic. And let's see.
Well, I just saw that AMEK is cyclic, but I don't know how.
AMEK.
Yeah. And I just think that maybe that BCEL form a harmonic conjugation, or BEML, I don't sure.
What are the 4 points?
Like wait, let me think of it.
Okay.
Oh yeah, BCLE.
B, C, L, and E, but you think are harmonic.
Yeah, if we can prove that AMEK is cyclic, so that is harmonic.
Okay. Let's see how we can do that. Hmm. We project for K, maybe? Let's see. Or I guess it's I guess what we could do is it's the same as showing that BCAF is a harmonic quadrilateral. It almost looks like A prime is like the reflection of K, but I don't think that's true. Yeah. But yeah, if COPD were cyclic, can we use Rhimes' theorem to show somehow? I think we want to construct this point right here. So that would mean POD would equal PCD, but POD would be PC. So that would mean PCD. I'm confused. PEG. Okay, so we wanted to show that. So you said AMEK is cyclic if BECL is cyclic, right? That's what you were seeing, right?
Yeah, but I don't know if that's gonna help.
Okay. BECL is harmonic by projecting through A. That's the same as saying that BA prime CK is harmonic, right? So I think that would mean we draw KE. I wonder if I think KE, yeah, it looks like KE and LA prime concur on this circle. I don't know if that's just an angle chase.
Well, it look like AF is the AC median.
Oh, okay. That's interesting. Oh, that would mean ABF. Oh, well, yeah, because like it's equivalent, yeah, to ABFC being harmonic. So yeah, F would be the median. What if we take BMC infinity and we project it through D onto AO? So then we get A, well, or maybe AM. Yeah, I wonder if we can redefine a lot of things in the problem. So maybe we could start out letting F be the intersection of the ace and median. Then we can like start defining the other points from there. That might be easier. That's kind of weird. So wait, we're showing that PCOD is cyclic. I mean, that's the same as saying, like, by symmetry, that would mean POB. Because E is defined symmetrically with respect to B and C. And then K, so is K. So basically, if COPD is cyclic, then I would think that BOP, if we let it intersect AC at a point, then that would have to be parallel also. Yeah, so it's like we'd also have to have BOGP is cyclic, where and this whole thing would be like parallel. And so then this would be like an isosceles trapezoid, basically. BOGH. So and do those intersect on the symmedian? No. Interesting. Okay. Try this. Let's see. But yeah, this problem looks familiar, and I think last time we did it, we might have done something where we make like an isosceles trapezoid. So I think it might have been like we made this point And then this was an isosceles trapezoid, but I just don't remember what we did after that. So I doubt that that's tangent. Just try it out. Yeah, it's not tangent, but that almost looks tangent, but yeah, it's not. So yeah, we could start letting F be the foot of the median. Then we could kind of pick an arbitrary point E on BC. So yeah, if F is the foot of the median and we pick an arbitrary point E on BC and we intersect FE with the circle ABC, then is it obvious that this is cyclic? So yeah, we could even pick a different point. Let's do that. Let's pick a different point on BC. And if we intersect FG with a circle, whoops, then I'm saying that AHME would be cyclic. That doesn't look right. No, AGMH would be cyclic. Yeah. So why is that? Is it just like an angle chase, or right? It looks like it has to be obvious, right? But I don't see it. So yeah, that's a very basic problem, but if you just take the foot of the median and you pick an arbitrary point on BC and you connect it, then you want to show that A, E, K, and M is cyclic. Same as saying OAM equals K.
Oh yeah, I think Y is AMEK cyclic. I know why.
You know why?
Yeah, so we have that the angle FEM is half of arc BF plus half of arc CK.
Okay.
And the angle MAK we can split into MAC plus KAC.
Ah.
And MAC is BAF, so yeah.
So that proves it. Okay.
Yeah, so basically AM EK is cyclic and it's just independent to the point P. So,
Okay.
but I still don't figure out why EKLP would be cyclic.
Yeah.
But is it trivial that F A prime L is linear?
I don't know. Well, I think it would follow from, because if we let F be the foot of the symmedian, then ABFC is harmonic. And so if you project those through A prime onto BC, then we'd get that BCE and this intersection point of F8 prime would have to be harmonic. But I think we can show that BCE and AK intersected has to be harmonic. So let me think about that. Forgot how it did that. Because if we intersected AK at a point, and then we projected those 4 points through K, then it would be B, C, A, and F. Yeah, so basically, yeah, we can prove that those are collinear by using harmonics. Because BCAF, what we're assuming is harmonic, so if we project through K, then that would mean that BC LE would be harmonic. And then we could do the same thing. And then if we project those 4 points through A prime, it would have to stay harmonic. So we'd have to have BC A, and that would, yeah. So these are collinear. And then we'd have to show that this is cyclic. Well, yeah, I mean, we could define P to be the intersection, but then, yeah, we have to show that that's cyclic. So we could do it either way, I guess. But yeah, I think we're close. So let's see. Yeah, we have to use that O lies on the perpendicular bisector. I don't think we've used that yet. But yeah, it's kind of interesting because Yeah, we haven't used that O lies on the perpendicular bisector, I don't think. So that's cyclic. And yeah, I mean, another way we could say it is we could draw the circle COP, and we could say let it intersect AB at D. Then we want to show it's parallel. That's another way to think about it. So if we did it like that, let's say we didn't know that this was parallel. We want to show OD is parallel. We would have angle COD. That would be 180 minus CPD. Just thinking. So angle ODC, we could try to show as angle DCB. So ODC is OPC. So we want to show OPC is OCB. So I think it's the same as showing OPC we want to show is DCB. Maybe there's like similar triangles or something. Well, let's see. Here's another way we could try to do it. We could try to show angle AOD as angle AEM. AOD is 180 minus DOP. I kind of like that, which is 180 minus DCP. So then we want to show DCP is BEP, which yeah, we're close. What about this? We want to show angle MKL is DCP. See what we can do. So we want to show AOD is AKM. Yeah, D is just such a weird point because it's like not symmetric. So that's what makes this hard. Yeah, if D were like symmetric, but it's like you're taking a parallel and you're just intersecting it with AB. So but what about this? So DO is parallel to BC is the same as saying DOB equals OBC, which is the same as OCB. I think that might be helpful. So we want to show DOB is OCB. And are there any like similar triangles that we can use? The weird problem. All Are GA and GF tangent? I think I already did this before. I don't think they are, but yeah. I think if we do it this way, so we would want DGC equals O, so DG and OB would be parallel. Right, that's weird. I don't think that's true. Right. I feel like it's just something simple that we're not seeing. Let's see if there's anything special about D. So are there any other ways of seeing this is cyclic? Can we use the power ratio lemma? I don't think so. Power of a point. What if we drew the other intersection of AB with that circle? Like maybe there's another point on the circle, DO, CP, and I don't know this point. Just waiting for this to go away. I'm not so sure about that. DOCP. I mean, we have this point right here. And it would make an isosceles trapezoid. Or any other point on this circle. Intersecting this or this. I'm just looking for other possible special points that could. I don't think that one does much. Maybe that one. It's linear with F and M. No, it's not true. Yeah, I am stuck. See what time it is. We have like 6 more minutes. We want to show DOBG as a parallelogram, right? So, and M is the midpoint of BC. So MH going to be parallel to DC. Yeah, I don't know what I'm doing. Okay, so if we define D to be where the parallel meets it, then angle DOP is 180 minus AOD, which is 180 minus AEM, which is AC. And we want to show that's DCP. DCP. Is there any way we can break it up? Maybe DCP is DCA? What? I don't know. So we want to show BEP equals DCP. So wait a sec. That's the same as saying it's the same as saying PEL is like PCG. point. Yeah, don't know. All right, so we are just about out of time. So yeah, thanks Pascal for sticking on for the whole time. And for everyone watching on YouTube, thanks for watching. So if you want to join us in the future, feel free to email me at mgreenb801@gmail.com. It's in the description of my video, and we meet every Sunday at 8 a.m. US Central Time. So thanks again and have a great day. See you next time.